we figured out what will be the in submargin classifier, what will be the optimization problem, and what will be the constant. Now we understood the nuance of this xi, what like why xi is introduced and why xi is part of the optimization problem also, and what is the meaning of C. Okay, so this we understood. Now to solve this optimization problem, we need to know something called primal and dual. So this is called like we can solve this optimization problem the way it is, but this is little bit complex and this is cost ineffective. So I'll show some examples why it is cost ineffective towards the end of the class. So for now, take it for granted is this is cost ineffective. We have to make it like this optimization problem a little easier. For that, we need to know something called primal dual. So what is primal dual? This is an important concept in convex optimization. So you guys don't have much idea, but I'll just give you a little prior about it. So you can read about it in detail later. So given this optimization function, minimize fw for the parameter w. So what does this say? You have to minimize this function fw. Listen to me carefully. This is very important. You have to minimize this function fw and find what is the w that is giving the minimum value for that f function, right? So this is what this minimization fw for the parameter w tells us. Now there are some constants given to us. So this is the setup for the Lagrangian variable. So the constants will of this form. Either there will be a function hi with same parameter w that is less than or equal to I, and there are let's say k constant of that nature, and there are some l constant. Sorry. Okay, so I'll put this p constant. So there are some p constant of this nature, li w equal to 0. So there are some equality constant, some inequality constant. Inequality constant we can either write in greater than equal to or less than equal to, but the way the mathematics has been introduced, that is in the nature of less than equal to. So given in greater than equal to, we can easily convert into less than equal to. Okay. Then what is the Lagrangian of this kind of primal formulation? So to introduce Lagrangian, how to introduce two more variables. One variable for this constant, one variable for this kind of constant, equality and inequality. Let's say alpha is the constant for the inequality and beta is the constant for equality. Now the Lagrangian will be, it will have three parameters, w, alpha, beta. So Lagrangian we can write like this, fw summation of I alpha hi plus beta I li w. And only constant we are concerned about is alpha I greater than or equal to 0. This is the only constant on this Lagrangian. So why this alpha I greater than or equal to 0 constant we are putting? So let's discuss about that first. So what's our goal? So this is the new function we got, and our overall goal is to minimize this fw. So earlier also we last class also we briefly discussed why we want to have this constant. I'm reiterating. So if you don't have this constant, let's say alpha, because we know hiw is less than or equal to 0. This we can ignore completely because this summation will be 0. So if hiw is less than or equal to 0, if alpha is also less than or equal to 0, this multiplication will be positive, right? So this multiplication is positive, and we can, if sometimes it can go to infinity also. So then it will not like achieve our goal, because our goal is to find the minimum fw, right? So whatever the value of this, if we try to minimize this L function, it will not give us this minimum fw. To get get rid of that scenario, we are putting the constant alpha has to be greater than or equal to 0. Now under this constant, whatever the value we will get, so what we have to do for this particular alpha I and beta I, so this first we have to optimize over alpha I beta I. That's what Lagrangian tells us. First optimize over alpha I beta I. You find the maximum value of this Lagrangian where and corresponding alpha I beta I. Once you found out this, now minimize over w. So you are doing optimization in two steps. First, trying to maximize this L for alpha I beta I, but so you cannot maximize like kind of in a way that this function will grow till infinite, right? If you maximize the function in a way it will grow till infinite, then you cannot find the minimum w. So for that you have to put this constant. So now let's see what happens, like what will be the possible value of this Lagrangian function L w alpha beta. So if everything is correct, like all the parameters, like the constants are satisfied, hiw is less than 0, liw is equal to 0, then it will be fw. So the value of this Lagrangian will be fw. Let's see how. So if this this constant is not satisfied, the first function, hiw is less than or equal to 0, if that constant is not satisfied, if that is greater than or equal to 0, and we have not put this restriction. So if you ignore this restriction and just say, okay, this constant is not satisfied, what will happen? So we can, if HIW is greater than 0, we can have some positive alpha I. So because there is no such constant, if we can have some positive alpha I, and this sum will go to infinity, right? So that's what that's what will happen if this constant is not satisfied. It will go to infinity. And similarly, for if this constant is not satisfied, let's say this is not equal to 0. If this is not equal to 0, sometimes it can be also very highly positive. If this becomes also highly positive, beta I, there is no restriction, right? Beta I also we can put some very high positive value. This will also go till infinity. Our overall goal is to minimize the function for the parameter w, right? So this is something we don't want. We don't want. Right? So this is what we want to get, FW, the minimum FW we want to get. When we'll get, if this constant is satisfied, this constant is satisfied, and this constant is satisfied, right? So like completely favorable scenario, right? Under favorable conditions, like this constant, and this constant are satisfied, LW alpha beta will give us FW. Everybody understood that point, or there is any doubt? So under these conditions being satisfied, three conditions, LW alpha beta will give us FW. Any doubt there? Anyone? Yeah, second term, that's what I said, right? If second term is not satisfied, when it will not be satisfied, either this is greater than 0 or this is not satisfied. No, so this is that's why we're solving this maximization problem, right? You have to maximize LW. You have to maximize LW so that it will come equal to. If we make it positive, you cannot maximize this. If you make it positive, maximum value will be infinite, right? So you have to maximize this function under this constant, then minimize over W. That will give us FW. Understood? You guys understood his route? He was saying if even if these conditions are satisfied, how will get LW equal to FW? If these conditions are satisfied, this can become negative, right? If both conditions are satisfied, this condition and this conditions are satisfied, this total multiplication can go to very negative. But that's why we have put this maximum optimization function. So to maximize this, then minimize, then it will give us FW. Okay, so this is very important. Now, but this is called the primal solution. That's what I have written here. P star equal to minimum W first. So you have to maximize, then minimize over this LW for LW alpha beta. But this is cost ineffective. That's why we try to solve something called dual of it. Dual of it meaning just to you exchange this maximum and minimum. So D star will be just try to minimize over W, then find the maximum alpha beta. Right. So this is cost effective. Why it is cost effective, we'll see. So there is now just understand this is a dual of it, right? So why this nomenclature came, all these things beyond the course of like the our syllabus. So there is two more important concepts we need to know to find the like to solve this optimization. There is one is weak duality, another is strong duality. So this is a this is a theorem. Always under any condition, D star will always be less than equal to P star. So this is again I am not proving. This will take another 1 or 2 classes. So I'll provide you the pointers. Weak duality says D star will always be so not weak duality. The concept of primal dual always says the optimum of solution will get using dual will always be less than equal to optimal solution will get using primal. Right? But the weak duality happens if D star is less than equal to P star, or you can say D star is less. Strong duality is when D star P star equal, both of them are equal. So this is what we are concerned about. So we want to find a scenario where D star and P star will be same. So when this both of them will be same, like you found some solution using primal and you found some solution using dual, both of them are same solution. So that will hold when the setup, all this optimization problem setup satisfies something called KKT condition. KKT condition. So what are the KKT conditions? So KKT condition says, so whatever our L we got, if you kind of take partial derivative with respect to W, whatever the parameters we have, So currently I'm considering the hard margin classifier. So if you have soft margin classifier, we'll have to also derivate over the xi values, right? So if whatever the parameter we have to take the partial derivative of Lagrangian with respect to those parameters and equal to 0. So these are the KKT condition. Again, how the KKT condition came, when KKT condition is satisfied, why D star equal to P star, all these proofs are beyond our syllabus, so we are not discussing them. So the thing is, we have to satisfy this KKT condition. To satisfy this KKT condition, so we have to this 3, 4, 5 conditions. I have put 4 conditions. There are 2 more conditions for soft margin classifier. For soft margin classifier, also you have to derivative over first take partial derivative with respect to xi. So that is another condition. Another condition is this has to be 0 for some I. For some I. And this has to be always greater than or equal to 0, alpha I. So when so what does this third point says? This third point is very much important in the perspective of SVM solution. What it says, for some I alpha I hi w equal to 0. So we have put hi w restriction so that it is less than or equal to 0. Right? If hi w is less than 0, how can this be 0? Only for the scenario if alpha is 0, right? So for which point? See, this I refers to the data points, like the input instances, right? When alpha I will be 0 to make this satisfied, because we are saying this is for some I, right? So if you see the SVM solution now, so at for which points alpha will be 0? For the points that is not the support vectors. For the points that is not the support vectors, alpha will be 0. So that's what the SVM solution tries to find out. So major goal is to have to find these support vectors, right? So if this condition, KKT condition satisfies, there will be some data points for which alpha will be 0. They are not the support vectors, clearly. Okay. So again, how it will find out this? They are the algorithm steps during optimization. It will automatically come out. For some of the data points, alpha will be 0. They are not the support vectors, and for the support vectors, alpha will be greater than or equal to 0. Right? So greater than 0. Not equal to 0. Overall alpha is greater than or equal to 0. For some I it is equal to 0. For some I it is greater than 0. So this is the KKT condition. Under this scenario, now we'll solve the optimization problem. Okay. So now what we do? We'll solve this dual problem. So in dual problem, what we have to do? First, optimize this L with respect to W, then with respect to alpha beta. So with respect to W, meaning we have to satisfy this KKT conditions, right? W I have written, but there are other parameters like all the parameters W comma B, whatever the parameters, right? Okay, any doubt there in the dual formulation? Again, KKT condition, I just gave you the overview why KKT condition is there and what it is, and what is the significance in terms of support vector. So how did it come? What is the proof of it? It's beyond our syllabus. Any doubt? B is this, we have this function is with of parameter W comma B, right? Or in soft margin classifier, it is xi also. 3 parameters are there, right? So the KKT condition I have written is for the hard margin classifier. If you write for the soft margin, there will be another condition, del L by del xi. That is also equal to 0 for soft margin. Okay, now we'll continue with the soft margin classifier because that will give us the optimal scenario irrespective of the fact that we have outliers. So this was our optimization function that's what we wanted to minimize, and this is our condition, right? These are the constants. So now we have to convert this constant into less than equal to, and this is already in less than equal to format. 1 second, I'll is the point. Yeah. So this we have to convert into less than equal to. So if you convert into less than equal to, this will look like this: minus yi into whatever W transpose xi plus b or W0 plus 1 minus xi. And you have to have this Lagrangian parameter for this, let's say alpha I, and this is mu I. So you ignore this second condition, mu I greater than equal to 0. There is no constant on beta as we saw here, right? Only condition is on the alpha. So I will modify the slides before uploading. Okay. So this is our now the primal setup. Now we have to convert it into dual. So to convert it into dual, what do we need to do? So just exchange the min max and first do the minimization over W. Yeah. So to do the minimization over W, we have to satisfy the KKT condition. For satisfying KKT conditions, you have to take the derivative with respect to all the parameters. So if you start taking derivative with respect to all the parameters, so this will what we'll get with respect to W. So optimal W star will get this. Again, this you can do on your own. Then with respect to B, this will be the solution we'll get, and with respect to J, this will what the relation will get. Now we'll use this relation to find the optimal kind of the solution to this whatever the minimization problem at hand for us, right? Now if you put all those values in the original optimization problem, this is the original optimization problem, and with this constant after converting them to Lagrange. So this is I equal to 1 to n. So this there are two images I have overlapped, so I'll correct it. So now if you put the whatever the W star we got, whatever the relation we got, these two relations, if you kind of replace them in this equation, so W star, if you see, I've already replaced it by whatever alpha I y x I, that is transpose again into this thing. Then if you see here, okay. If you see here, what is happening? Mu I plus alpha I equal to C. So wherever this mu I alpha I terms are there, they will get nullified. So this is mu I minus Ji, alpha I minus Ji, and Ci minus Ji. These blue circles will get nullified. They will boils down to 0. Whatever remaining terms we have, alpha I, just the alpha I, because this is alpha I minus alpha I Ji. That is when merging with mu I Ji and Ci Ji, they are becoming 0. So remaining term is alpha I here, the summation of alpha I. And this always this also we know, this summation of alpha I yi equal to 0. So this will also boil down to 0. So only remaining term is this transpose this plus minus alpha I yi transpose xi and just the alpha I. These are the remaining terms. So now if you kind of try to merge these two things, so this is half into W transpose W, and this is summation of alpha I yi W transpose xi. So if you merge these two things, so you will get minus half into summation of alpha I, alpha j, yj, xi transpose xi. So you can try to kind of solve this on your own, because this, if you multiply this, if you will get alpha I, yi, alpha j, yj, xi transpose xj, and there is a half here, and this is minus 1. So if you merge these two things, you will get minus half, and alpha I, alpha j, yj, xi transpose xj. So this is the culmination of these two terms. And only remaining term is summation of alpha I, right? That's what we have got. Other things are nullified to 0. Now this is our the dual optimization problem is you have to just maximize that whatever function we got over this whatever the Lagrangian parameters. Okay. So now this you can solve using quadratic problem. So quadratic programming, again, that is beyond our syllabus. How do we solve that maximization problem using quadratic programming? And that's quite like kind of quite effective and quite cost effective. So this again, I am not telling you how do we solve it. So this again, I'll give you the pointers. So just understand, optimizing this function is quite cost effective than whatever the optimization function we have original, the minimization of half into W transpose W by summation of Ji. Okay, now major goal is, so if you see there is no W involved here, right? So if there is no W involved, how will get the optimal W? So now we have to use the, you have to come back to this KKT third condition. So our optimal final goal was to have get this final W that will separate these two classes, right? Now in the optimization problem, if you see, maximizing over alpha I, alpha j, yi, yj, x transpose x, there is no W involved. So how do we get the optimal W? So what we get from while solving this maximization problem, which alpha I are 0 and which alpha I are non-zero, right? So we are not trying to find the W explicitly here. We are trying to find out which support vectors, which data points are involved in the support vector computation. Let's say these two are involved, and here this is only involved. So this only for these three data points, alpha I will be not equal to 0, others are equal to 0. Now if that is what we know, then just we can find the summation alpha I, alpha j, xi transpose xj. This summation will give us the W. So we don't need to find explicitly W here. We just need to find what are the alpha i's, they are non-zero, what are the alpha I, they are 0. That's what this optimization function will give us. After that, you just multiply that alpha I with corresponding xi, alpha j with corresponding xj. then that summation will give us the optimal W. That's the solution of SVM. Any doubt? So we're not trying to find explicitly W here. We have already minimized over the all W values in this step. Now we have to we are going to the second step of the dual, that is the maximizing over this whatever the function that is left over, and that will give us which alpha I, alpha j are 0. That's all. Any doubt? Okay. So now what happens in the testing scenario? So during testing, so we know okay, so we got the optimal W. During test time, how we'll decide whether a point is belonging to this class or this class, right? So for that, again, we don't care particularly about the W. So what we care about is which alpha I is. So okay, so what is the dust? I'll use this board. So during test time, let's say we have a data point x star, right? So like ideally, what should happen if we know the whatever this classifier line? Let's say that's W. So what can we do? W transpose x star plus b, kind of sigmoid of this. Sigmoid of this. If this is greater than 0, then this is plus 1. This is less than 0. This is minus 1. This is ideally what we expect to do, right? So we find W transpose X plus B. So whatever the sign of it, right? So that will give us the which class this data point belongs to. But we don't have the explicitly W. We don't have, right? So in that scenario, what we'll do? So what we know which are the support vectors. So we know support vectors are, let's say, some alpha is. Some alpha is a support vectors. We know the corresponding data points, input data points during training. So that's let's say there are the training data points xti, right? So that's what we just will try to figure out which alpha is are part of the support vectors and what are there during training time. What are the input data point? We'll just multiply that with x star, then plus b, sigmoid of it. If this is greater than 0, this is plus 1. If this is less than 0, this is minus 1. That's what we'll do. We don't explicitly use W here because we don't have the explicit W. We only have the alpha H and the corresponding training data point, right? So that's what it is converted into. So you can you apply this equation, this point into this equation. But in the end, what we'll do, we'll just multiply with this corresponding alpha and xi, and yi is there, whether the data point original was belonging to class 1 or minus 1, plus 1 or minus 1. Okay. Understood what we do in the testing scenario? There is yi here. Because this yi will give us whether it is plus 1 or minus 1, right? So this multiplication is also important. Any doubt during test time what we'll do? Take some time to sink in all the setup. First, we try to, our main goal was to optimize this first function minimization with under this constant. So we decided, okay, this is optimizing, this is again cost ineffective. Why it is ineffective, we will discuss right now. Then we wanted to convert it into something called dual. We converted it into dual for corresponding dual problem, and we wanted this strong duality. For the strong duality to hold, we have to satisfy this KKT condition. For KKT condition, we have to optimize over the corresponding parameters. First, we optimize over the corresponding parameters using whatever the resultant equations, relations, or resultant W's you are getting. We'll put that into the minimization problem. And after putting them into the minimization and simplifying, we will give another optimization problem that will help us to do the final optimization over this D star for the D star, right? And D star will give us optimal alpha is and corresponding yi and xi we know, right? Using optimal alpha is, optimal alpha is meaning alpha is corresponding to support vectors. Using that, we will find the whatever the linear classifier we have, right? Then during test time, given a data point, we know what are the alpha is that they are the support vectors corresponding yi and xti, and then we'll do this sigma over this multiplication. Then that will give us the class level. Again, but when you perform this using, let's say, xscalon package, all these things are abstracted. You don't do explicitly primal dual conversion. You don't do a Lagrangian. You don't do KKT. All these things are already taken care of by the convex optimization package of scalar. You just call the SBC or SVM, whatever the classifier, and automatically it will give you the class level or plus one or minus one. Okay. Any doubt on the mathematics part? All clear? Should I go ahead? Okay. So now coming to kernel trick. Now we understand why this original optimization problem was cost ineffective. So this is one beautiful scenario we discussed. This is very easy. The data points are linearly separable with some outliers. There was one outlier here, one outlier here, one outlier here. Right? So still, if we run our optimization problem, what this KKT condition will do, it will not, it will assign these outlier points. The weightage, the alpha I corresponding to these outlier points will be 0. That's how we'll be able to ignore these things and try to find the optimal support vectors that will give us the W. But if the data points are like in this kind of nature, they're not not linear at all. So whatever you do, you cannot make them linear. So in a way, so if you see this data, so the first graph, if you see, if you forcefully do it linear, so either you misclassify some data point or you have wrong belief about some data point that is already given. So if let's say these data points are in class 0, if you forcefully make this as a linear classifier, you are believing that these points are wrongly classified and they're in class 1, right? So that will change our belief about the training data point. But training data point is like this only. So this is the nonlinear training data point given to us. So we cannot change our belief about the training data point. We have to learn a nonlinear classifier here. So how do we learn a nonlinear classifier? SVM without kernel trick, whatever the trick we'll learn, without kernel trick is just a linear classifier. It cannot do nonlinear classification. And this is just a binary classifier. SVM is originally, by definition, by construct, it is just a binary classifier. Okay. So in quiz, there will be a question, how do you convert this binary classifier to multi-class classifier? I'm giving one prior question, but you can come prepared with this. How do you convert this binary classifier to multi-class classifier for SVM scenario? Okay. So I'm giving you beforehand, but this question will come. Yeah. So so what we try to do first is again the binary classification, but in non-linear setup. To do it in non-linear setup, so one thing we can do is if you visualize this. So if you visualize these two classes, I don't have the other. Okay, let's discuss about the circular data. So if you visualize these two classes, so this is concentric, and this is little far from the center. If this is the center, now if you know what is the normal like kind of bell curve, the normal distribution. So what happens from this center, these data points are the variance of these data points are low, and for this data point the variance is high, right? So if you try to project into high dimension, what will happen? So all these data points will come here, and all these data points will come here in the high variance region. This data point will come to low variance region. Now, if we know these things, now you learn this hyperplane. If you project into, let's say, high dimensional scenario, these data points will come up, and this the high variance data points will lie below. Now, this in high dimension scenario, we can learn a kind of hyperplane to distinguish these two classes, right? That's what the kernel trick does. So projecting the two-dimensional data points that are in nonlinear setup to into high dimension where it can be linearly classified using some hyperplane, not like kind of a line or a plane, right? So that's what we are doing, explicitly transforming data into high dimensional space, use a kernel function to compute the dot product in the space effectively. So these two plots, when we can see like, okay, so this is very easy. So we can visualize, okay, you just project into some, if it is 2 dimension, you project into 3 dimension, you can do it easily. But there are some complex functions that are not easily doable in just 3, 4, 5 dimensions, like projecting them into 3, 4, 5 dimensions. Sometimes you have to project into 1,000 dimensions, 10,000 dimensions to actually find the correct linear classifier. So under those scenario, if we perform the primal, what will happen? Right. So if you are transforming data points into very, let's say 10,000 dimensions, so this W will have a 10,000 parameter, 10,000 values, right? So this W transpose W, this dot product will be quite expensive. This dot product operations are quite expensive. So this will be quite expensive, and optimizing over this will be also quite expensive. So how this is helping us in the dual, now we'll see. Okay, so what is the kernel trick telling us? Again, there are some theories written here. You can go over the slides later. So original data points were in small dimension, small d. Now we are projecting them into capital D. So given n training data points with small d features, so small d is quite less as compared to capital D. So whatever for the slide reference, you can note it down. Small d is quite small as compared to capital D. Okay, so originally D features were there. You are explicitly transferring them into higher dimension to make them linear in the higher dimension. This transformation will take order of ND computations. Now then computing dot product between two transform vectors, whatever transform vector is in capital D dimension, that is order of D, because the dot product you have to multiply each element with each other element in the corresponding index. Now training explicitly, like SVM solver will take order of n square D computation, and in worst case. So if you do by the primal solution. Now how do we reduce in the dual, we'll see. Right, so sometimes D can be very, very large, particularly in RVF kernel, when we'll discuss what is RVF kernel. This RVF kernel that uses this, again, the bell curve, the normal distribution, it is infinite. So the dimension is for the RVF kernel is infinite. So this computation will be really large. Sometimes it cannot be solved also in linear time. Not even linear time, in quadratic time also you cannot solve. So what does kernel trick do? So it finds a kernel function. So kernel function, what is a kernel function? Kernel function is a kind of a matrix you can consider. So I'll erase this board now. So start from there. Okay, so what's a kernel function? So imagine this is a matrix, and on each row these are some xi data points. So input data points I, input data points j, like this you have n data points, and on column also you have same data points I, j up to n, right? So what each cell of this kernel matrix is doing, this is a something called kernel matrix. Kernel matrix. Yeah. So this what each cell of kernel matrix is doing, it's something called what will be the value of this each cell in the kernel matrix? This is computed by something called kernel function. The kernel of xi comma xj will be dot product between transformed xi comma transformed xj. So this is what the what each cell of kernel matrix will look like. Okay, so this is the dot product between transformed xi and transformed xj. Right. Right. So this dot product computation in high dimension, we can do it in original feature space. Original feature space in the sense the feature space of D. Right. Even if you are transforming into the high dimensional space, before transforming also, we can do this kernel computation and do it in small d dimensional space. And then the SVM training complexity remains in n square d. So what happens, whatever the primal dual you are doing, it will always take n square d if d is the dimension of the input data point or whatever the data point you have. So now if you convert them into this kernel matrix, and each cell of the kernel matrix is, let's say, this particular value, and to fill this each cell you need order of d computation. Then you have the data point that has kind of d dimensional space. This will be a vector of d dimensions, whatever the value will get for kernel function. Then you compute this primal dual, and it will give us n square d complexity. So what are the different kernels? So again, why it is order of D, now we'll see why it is not order of capital D. What we are doing, we're not explicitly transforming them into the higher dimension and doing the dot product. So it says like without transforming them into higher dimension and doing the dot product, you do the dot product in the same original dimension itself and fill this kernel function. That will help, that will do the job. So what, let's say there are some kernels I have written, generally we'll use any of these kernels, not beyond this for your concern, but for research purpose, there are more kernels also. So what's the linear kernel do? It will, instead of transforming the data point into high dimension, both the data points into high dimension, it will just take the dot product between xi and xj. Again, xi, xj, we know they are in d dimensional space, small d dimensional space. This dot product is order of d, right? So if you do the linear kernel, how do you fill the kernel matrix? You take every pair of data point and do this dot product, right? For every pair of data point. Again, because you're doing dot product, and dot product is kind of like transpose invariant, like xi dot product xj, xj dot product xi is same. So it will be a symmetric matrix, right? Then coming to polynomial kernel also, this is this operation xi transpose xj plus c, this is order of one time. Sorry, this is order of d computation, and taking power d or p, whatever it is, this is order of one. So this computation can be done also in order of d time. Similarly, radial basis function, the RBF kernel, this particular L2 norm you are computing x1 xi minus xj, this is order of small d time, because you are doing in the original space, not in the transform space, and overall will be order of d. Exponential is order of one. Then sigmoid kernel also similarly, all this dot product is order of d, tan h is order of one, right? So this I have broken down why it is order of d for every kernel function. So you can go over it. Now how this kernel trick works to save the time, particularly in the computation. Again, because instead of transforming them into higher dimension, you are doing this computation in the lower dimension space, the original dimension, then filling this kernel matrix, and using this kernel matrix. Now what is our training data point? This one triangle of this kernel matrix, not all the data points now, right? So using this, so why it is just one triangle? Because if you go back to this particular formulation, this maximization problem. So if you see this maximization problem, what you need to know, you need to know this particular thing, right? Xi transpose xj in the optimization problem. You don't need to know anything. So that you will get it from the one triangle of the kernel matrix. So you just replace this alpha say xi transpose xj by okay, I'll write here. So you replace this xi transpose xj to alpha phi of xi transpose phi of xj, right? So this is what you are replacing. So during kernel trick, this mathematics will just change to, instead of xi transpose xj to alpha phi of xi transpose xj. But what is this phi of xi transpose xj? Because of the kernel trick, this is just the entries of this kernel function, kernel matrix, nothing else. So once kernel matrix is computed, so kernel matrix computation, each entry takes order of d time. So you don't need to do it for every pair also. So optimization problem will help you to tell ki, okay, I don't need to do this computation for every pair. So whatever the alpha is are non-zero, it will do for them only. Once you do that, you just replace those corresponding whatever ijth index from the kernel matrix here. Then you optimize over this. Right? So this is what the kernel trick do. So now what is the advantage of dual over primal? Right? So in the primal, if you see, we wanted to particularly kind of solve this Lagrangian. And in dual, we are solving this Lagrangian. So Lagrangian has this Lagrangian parameters, but in the primal, we have this optimizing over W also, right? So why it is helping us? Now we're using this dual formulation, we're getting rid of this high dimension, that is the W, right? So because we are able to get rid of the high dimension in the dual formulation, that is helping us to because already the computation takes n square d, whatever the d it is. But in the dual, we are getting rid of the high dimensional d, but we are able to do it in the low dimensional d also, right? But in the primal, already the w is involved. W is in high dimension if you're transforming the data, and this will kind of incur high computational cost, right? So that's why dual is cost effective than primal. Any doubt in the kernel trick? How do we do? Again, during test time, how do you apply the kernel? So let's say there is a data point given to us that is extra, right? So during test time, what you have to do? This because we don't have this kernel matrix for the test data point, right? You have to explicitly compute this computation, whatever the kernel function it is. If it is linear kernel, just the dot product. If it is not linear kernel, you have to find the corresponding whatever RBF kernel. This computation you have to do with each data point that is part of the support vectors during test time. During training time, you take it from the kernel matrix, but during test time, you have to compute this thing particularly. Again, this is not xt and extra star during for kernel trick. It will be phi of xt, phi of extra. Okay. Any doubt? Yeah. Yeah, sometimes there may not some high dimension exist, but general theorem is if you project into very high dimension, there will be some linear classifier. So that's basis on that theorem only neural network works. There will be some very high dimensional space. Neural network also, when they do classification, they do in, let's say, a million dimensional space. There is some high dimension where you are able to classify the data points. There will be. Mhm. Yeah, this is experimental. Like we don't know, like just looking at the data, real world data, we cannot see which what is the actual dimension of the high dimensional space. We have to experiment. Let's say try with some 10, then try with 100, go in the power of 10. You see between 1,000 and 10,000, you are seeing some number. Then you kind of again do the hyperparameter search between 1,000 to 1,000, 1,000 to 2,000. You go like this. That's the hyperparameter only. What's the dimension that we cannot see from the data points? Any doubt? Okay, so this is all about your SVM theory. So I'll just show you few codes that will help you to solve some problems in the lab session. So how much time I have? 19 minutes. So the next course plan is next week, logistic regression and HMM will be covered on your next lab, not today's lab. Next lab will be having problems on SVM and logistic regression. Okay. Then we'll see what to do about next to next. But maybe linear regression and k-means will cover. Oh, sorry, decision tree. Okay. Okay. So just I'll just show you some starter codes again. The assignments that will be asked to that will be asked in the lab session will be little different from this. Yeah. So here what I so not this one. So there are some plots I was trying for your visualization purpose only. Okay. Yeah. So what I have taken is let's say some random data points x1 x2 here that will give us data points from cluster 1 cluster 2 or like positive class negative class. So generally this is how we'll run the SVM or SVC classification that will be given to you in the class, but this randomization will be taken away. So I'll give you explicit data points for x1 and x2, and like you have to reason for particular x1 x2 type why a particular kernel works or why a particular dimension works. Okay, so that will be the majorly your assignment, but there will be some new things so that I am not talking now. Yeah, so given data point x1 x2, so correspondingly like for one class you mention it as -1, one class you will mention it as +1. Again, this is the transformation. Again, this you can do on your own, try out without transformation what happens, with transformation what happens. So now what you need to do is just call this SVC class. So all the primal, dual, all the Lagrangian that is abstracted out, that is there in the SVC package, you just call this SVC class with some parameters. So here in this particular code, there are only two parameters involved. What is the kernel and what is the C value? There are so many parameters in the SVC class that that will be asked in the lab session for you to explore, right? So you better go back and check what are the parameters of SPC and map it to the mathematics we have discussed. What is their significance and what will be the optimal value given a data point, given two classes, right? So you have to specify the kernel here and C here, and just do the call this clf.fit. It will give us the whatever the optimal W, right? From this you get the W and B, but this is again abstracting out what are the alphas for which we got the for what are the support vectors, right? In maybe an assignment you can be asked to figure out what are the support vectors given to cluster of the data points, right? So in this code you can see directly we have got the W and B, but using the dual, how do we get the W and B? Maybe this will be the part of your assignment. I am not explicitly telling, but again you can anticipate these questions. Then once you got WB, you are just this is a all these codes are for plotting, and this will like kind of this plotting code is taking care of how to circle it. Okay, so this will be the kind of overall code of the SVM. So I'll share this particular code for you to get started with, and there is another code. Yeah, so this is for the kernel trick. So you can try with instead of RVF kernel, you can try with let's say linear kernel, and you see how the classifier, the hyperparameter, sorry, hyperplane is being drawn here. Right? What are the W and B's you are getting? You can experiment on to figure out what are the alpha is that is non-zero, what is zero. So you can check it out on your own. Again, this is for concentric data that I discussed. Okay, so these three codes I will share for the concentric data and this particular curve and these three things. Okay, so based on this code only, there will be some new questions on the lab system. Okay, that's all for the SVM. So any doubt, feel free to ask me, or I don't see anybody using Teams particularly for asking doubts. If you have any doubt part of AI, ML that is being covered in the class, feel free to use Teams. There are so many TAs, they will answer you. 20 TAs are involved. So use the Teams forum effectively if you have any doubt in the math or anything. Okay. Okay, and today there will be the mid-sem papers will be shown to you. You just come and take the photos and go back. Free form will be open later. Okay, that's all for the today's class.